Hello and welcome to our webinar. The topic we will be presenting today is chill beams to reduce or eliminate reheat. My name is Nick Searle and I will be presenting today's webinar. I'm a chief engineer at Titus with 25 years industry experience, 15 of which I've spent specialising in air-water systems. I've been fortunate to have been involved with several landmark chill beam projects across the country, including one of the first healthcare buildings in the USA to use active chill beams, Moses Cone Hospital in Greensboro, North Carolina. In today's webinar, we will start with a brief look at an energy use case study of a North American hospital, and why hospitals and labs consume several times more energy than a typical office building. ASHRAE Standard 170 was updated in 2013 to include changes that potentially allow reheat to be reduced by using room recirculation terminals such as active chill beams. We'll look into how chill beams can be used in healthcare and labs to reduce energy consumption and cover some typical active chill beam system designs, layouts and control strategies. But before we start, let's look at ASHRAE Standard 90.1. ASHRAE Standard 90.1 provides guidelines for the design of energy-efficient buildings and generally restricts reheat, which is defined as to raise the temperature of air that has been previously cooled either by mechanical refrigeration or an economizer system. Well, that probably seems obvious to most of us working in the HVAC industry, but it wasn't to me when I first started working in air distribution back in 1996. I couldn't understand why it was necessary to burn energy cooling and then reheating air. I thought it was as crazy as driving a car with your foot on the gas pedal and the brake pedal at the same time. But reheat often occurs with traditional HVAC systems, as air is used to perform three separate tasks: ventilation, dehumidification, and cooling. This multitasking causes some problems. Some zones in the building may require high amounts of ventilation air and very little cooling. But the temperature of the air must be set low enough to satisfy the zones which have the highest cooling demands. So zone heating of pre-cooled air will now occur in the spaces that have low cooling demand to prevent overcooling. This frequently occurs in applications that have relatively high ventilation requirements, such as hospital patient rooms or labs. For much of this webinar, we will be discussing these two types of application. So how much energy is wasted by reheating air in a typical hospital? This case study commissioned by the Department of Energy gives us some clues. The National Renewable Energy Laboratory monitored the energy consumption of two hospitals, the Mass General Hospital in Boston and the State University of New York Medical University, for a period of 12 months. We've extracted data from the Sunny building to give you an example of how a medical building can burn through its energy. This Sunny building was opened in 1995. It's a 143,000 square foot building that spends most of its energy driving the HVAC fans, and a staggering 27% is consumed by the reheat loop. The monthly energy use data also makes for interesting reading, as the consumption of the reheat loop barely changes month by month. But these numbers are not surprising, as there are many other case studies on the internet that show similar energy consumption characteristics in healthcare buildings. What is surprising is that if 4% of all energy in the USA is consumed by hospitals, as claimed in this article titled "Energy Reduction in Hospitals," then reheat may account for as much as 1% of all energy used in the USA, and that includes transportation. So why is so much reheat energy consumed in hospitals? Well, if we analyse the loads and ventilation requirements of a typical sized patient room, it's easy to see why. Using a 300 square foot by 10 foot high patient room as an example, ASHRAE Standard 170 requires that 4 air changes per hour should be sent to the patient room whenever it is occupied. Of those 4 air changes, 2 must be filtered outdoor air and 2 can be recirculated. So for this size room, a total of 200 CFM is required, which includes the 100 CFM of recirculated air. Based on the moderate cooling load of 20 BTUs per hour per square foot, the total cooling load will be 6,000 BTUs per hour. Using this simple equation, we can calculate that 280 CFM is required to cool the space during its peak load condition. As the amount of cooling air is 80 CFM more than the required ventilation and recirculation air, a VAV unit would normally be used to vary the airflow between 200 and 280 CFM, but it cannot turn down to below 200 CFM. The air will be sent to all of the VAV boxes, typically at 55 degrees, to provide cooling across the building. The cooling capacity range provided by the air is 4,340 to 6,000 BTUs per hour, which is only a 28% turn down from the max to the min. Now, if the space cooling load falls below 4,300 BTUs per hour, the air will overcool the space, causing comfort issues. The only way to prevent this is to reheat the air at the VAV box to maintain the set point temperature. This example demonstrates the mismatch between cooling and ventilation requirements that can occur. Some zones in the hospital will require cooling due to high equipment and solar loads, so the air must be sent throughout the building at 55 degrees, but many zones will require little, if any, cooling at all, forcing the system to reheat. An effective method to reduce reheat is to decouple the ventilation and sensible cooling loads using active chill beams. Active chill beam systems have been used in Europe for many years and first started to appear in North American buildings in the mid-2000s. So how do active beams work? They are very simple devices consisting of a primary air inlet, rows of induction nozzles, an induced air passage and a heat exchange coil. This coil is supplied with hot or cold water to provide heating or cooling to the space. Primary air from a central air handling unit is sent to the active chill beam via a duct distribution system which pressurizes the primary air plenum. This primary air is forced through a series of induction nozzles which causes room air to be entrained through the heat exchange coil before mixing with the primary air from the nozzles. The mixture of primary and induced air is finally delivered to the room via a number of supply air slots. Active beams typically induce room air at a rate of around 2 to 4 parts per 1 part of primary air from the central air handler. Control valves regulate the flow of chilled and hot water in response to space cooling and heating demands. It is important to note that active beams are designed to provide sensible cooling only, with the latent cooling being provided by the central air handling unit, so the beams are piped with chilled water held just above the space dewpoint temperature, so the coils operate in a dry condition at all times. One of the primary benefits of chill beams is the fact that they rely on water to transport most of the cooling and heating energy around the building. Water is a far more efficient medium than air for transporting heating and cooling energy due to water having a higher density and specific heat capacity. This results in a more compact distribution system, as the same amount of cooling energy can be carried through a 1-inch diameter water pipe as a 16-inch by 16-inch air duct. This compactness and the fact that water is incompressible means that much less energy is required to transport heat energy around the building versus air. In a typical active chill beam system design, the air will transport around 30% of the sensible cooling, while 70% will be transported with the water. Active beams deliver the conditioned air in a similar manner to a conventional slot diffuser. The cooled or heated air delivered through the slots of the chill beam is thrown across the ceiling where the room air is entrained and mixed. Beams can be positioned above heat generating sources such as electrical equipment mounted on lab benches, so the rising warm air currents are captured directly into the induction grills of the chill beams. As most of the cooling energy is provided by the water system, Less riser and interstitial space is required for the service ducts and pipework, resulting in a very compact HVAC system. An all-air VAV system may typically require a 13-foot slab-to-slab spacing to achieve a 9-foot floor-to-ceiling height, compared to a typical active chill beam system that would need just a 12-foot slab-to-slab height to achieve the same 9-foot ceiling height. Alternatively, the ceiling heights could be increased by 12 inches with the same 13-foot slab-to-slab height. There are various styles and configurations of active beam available to suit almost any application. Shown here are just a few examples. This 24-inch wide beam shown on the left is the most common type used in North America. It's a linear beam that features a large horizontal heat exchange coil with 2 supply air slots either side. It's designed to fit into a standard 24-inch by 24-inch suspended ceiling grid. The 12-inch wide unit shown on the right is a slimline unit with a narrow profile for a more discreet appearance. However, it does have a lower cooling capacity than the 24-inch wide unit, so more are required for a given load. The modular beam shown on the bottom here is also designed to fit into a lay-in ceiling system, but this beam has 4 supply slots and is designed for smaller spaces such as private offices. Some active beam designs incorporate other services such as lighting into a single unit. These are known as integrated service or multi-service beams. This integrated service beam incorporates a dimmable, efficient LED light fitting in the centre of the unit and is particularly suitable for patient rooms where it can be difficult to accommodate all of the other services when the ceiling space is limited. Another good application is for laboratory alcoves. These rooms are usually small and often there is just not enough space to fit an active chill beam and the light fitting, so integrating the two eases ceiling coordination. In this next section, we will discuss how we can use active chill beams to reduce reheat in healthcare and laboratory applications. But before we get into the detail, let's see why the revisions made to ASHRAE Standard 170/2013 are relevant to the use of chill beams and reducing reheat. The first notable revision affects the air change rate in patient rooms, reducing the number from 6 to 4. The outdoor ventilation rate has not changed, staying at 2 air changes, which must be filtered at the air handling unit. A significant change is in the requirements for the recirculated air. The standard states that recirculated air within the same space now counts towards the 2 non-outdoor air changes. So this includes the induced air through fan coils or active chill beams. The standard also stipulates that recirculation unit filters will not be required on surfaces that are not designed to condense water, meaning sensible cooling coils such as active chill beams. So an active chill beam used in a patient room can be supplied with 2 filtered outdoor air changes of primary air from the dedicated outdoor air unit. The beam will induce at least 2 recirculated air changes from the room to provide the minimum total of 4 air changes back into the room. As a typical active beam unit will have an induction ratio of at least 2 to 1, in reality over 4 air changes will be induced from the room, providing a minimum of 6 air changes, so will easily meet the minimum requirements stipulated in Standard 170. If we apply this concept to our example hospital patient room, we can see how reheat can be reduced or even completely eliminated. The primary air is sent to the patient rooms from a dedicated outdoor air system supplying 100% fresh air with no risk of cross-contamination from the recirculation air. The primary air can now be sent to the space at a warmer temperature, typically at 65 degrees. The minimum airflow is now only 100 CFM as the primary air system is sized for outdoor air only. The maximum airflow is also 100 CFM as the airflow does not need to be varied to cope with fluctuations in cooling or heating load. Instead, the water flow to the chill beam coil is varied by valves to control the space temperature. The cooling range and turndown has now increased dramatically over a VAV reheat design. The minimum airflow of 100 CFM at 65 degrees provides only 1,085 BTUs per hour of cooling, and maximum cooling is delivered to the space when the chilled water valve is fully open. The turndown in this example is now 82% from maximum to minimum. Occupant comfort is also improved as the chill beam is providing constant volume air at a slightly warmer temperature than an all-air system during cooling, so is less likely to cause cold spots and drafts. One important point to note is that while the primary air can be delivered to the space at 65 degrees, it must be suitably dehumidified first to offset the latent load in the room, so is typically supplied at 56 grains or less. This warmer, drier primary air is usually delivered using air handling units with heat recovery wheels. However, if the engineer prefers to use conventional air handling units producing 55-degree primary air, reheat can still be significantly reduced as the patient room requires only half the primary air of a conventional VAV reheat system. When sized for the loads shown in our patient room example, a single 6-foot-long linear active chill beam is required and is usually installed towards the centre of the room above the bed. So we have seen an example of how using chill beams can reduce reheat in patient rooms, but can they be used anywhere else in the hospital? They can be used anywhere where room recirculation units are permitted, which is typically in the less critical areas of the hospital, such as radiology, labour, treatment rooms, and the X-ray suites. Most of the admin areas of the hospital will be subject to Ventilation Standard 62.1, so active or passive chill beams can be used in most of those areas. All of the critical areas, such as operating rooms, recovery, and intensive care units, cannot be served by chill beams, as recirculation units are not permitted. Now let's look at another energy-intensive type of building that can benefit from active chill beams: laboratories. The fact that lab buildings can burn through 5 to 10 times more energy than a typical office building won't come as a surprise to anyone who's ever visited one. The HVAC systems are often responsible for over half of the total lab energy consumption, as the systems are designed to strict ventilation requirements to protect staff working near hazardous substances. Depending on the lab use and classification, the HVAC systems will frequently be designed to deliver 6 to 10 air changes per hour, and additionally, labs where gases and chemicals are present must exhaust all return air. When designing HVAC systems for labs, we can break them down into two classifications. Labs that are fitted with a high density of fume hoods will require large amounts of makeup air delivered from the central air handlers to maintain the required pressure in the lab. These type of labs may require more than 10 air changes when all the fume hoods are operating, and are often referred to as makeup air driven labs. Labs that make extensive use of heat generating electrical equipment may have heat gains of up to 70 BTUs per hour per square foot, but often with lower ventilation requirements as there are fewer fume hoods. The ventilation rates may be as low as 6 to 8 air changes, but much more air may be required to cool the lab when the electrical equipment is in use. These are often referred to as heat-driven labs. With a minimum ventilation rate of 6 air changes, a cooling load and ventilation rate mismatch often occurs, so again reheat is applied to prevent overcooling the space during partial load conditions. Active chill beams have been successfully used in several laboratories across the USA to reduce energy consumption. We can demonstrate how they can be applied in this example of a heat-driven lab. This is a typical lab bay of 22 feet by 30 feet with a cooling load of 50 BTU hours per square foot and a ventilation rate of 6 air changes. 6 chill beams will handle the 6 air changes, with each beam sized for 110 CFM and typically laid out in 2 rows of 3, perpendicular to the perimeter wall. If we compare the system sizing of a VAV design versus an active chill beam design, the total primary airflow rate for the beam system is only 6 air changes compared to the 14 required for the VAV system. The VAV system is much larger as the air must also cool the 50 BTUs per hour per square foot of heat load. Neither system can turn down below the 6 air changes if the lab is occupied, but the chill beam system can be designed with warmer primary air to avoid reheating. Using 65-degree air as an example, the chill beam system delivers a minimum cooling capacity of around 7,200 BTUs per hour with the water valves closed, compared to 14,300 BTUs per hour for the VAV system. The chill beam system is capable of turning down further, so will reheat less than the VAV design. Positioning the chill beams in the ceiling grid can be challenging when coordinating the design with all other services that a lab requires, but generally the chill beams are located either over the Rs or over the benches. This layout shows aisle positioning and may be chosen when the ceiling directly above the benches is congested with services such as pipes, task lighting and electrical conduits. It's also easier to access the chill beam cores for cleaning when located above the aisles. Care must be exercised when locating chill beams near to fume hoods, as high velocity air thrown directly down the hood face will compromise the safe operation of the hood. It's generally good practice to use one-way beams near fume hoods and throw the air away from the hood as shown in this layout. One potential issue with this layout is that as the rows of beams collide the air streams above the benches, sensitive electronic equipment such as high-power microscopes may be affected by the air movement. If this is an issue, then the beams may be positioned directly above the benches, so the air streams collide away from the sensitive equipment and directly into the Rs where the occupants are. Positioning the beams directly above the bench equipment will also enhance the cooling performance of the beams, as they'll capture the convective currents directly into the induction grill. The only negative is that the coils are more difficult to access for cleaning, but this will be an infrequent requirement in a clean laboratory. An alternative layout that could be considered for labs with high perimeter heating loads is to use one-way beams rotated 90 degrees to throw warm air down the glazing to reduce cold downdrafts during the heating season. Lab storage freezers can produce a lot of sensible heat. So in this example, we've used one-way active chill beams that are located above the freezers to induce the convective heat currents directly into the beam coil. So all of the layouts we have shown so far are based on a typical heat-driven lab, with air change rates up to about 8. But how are beams selected for air-driven labs with higher air changes? If the beams are selected to handle all of the air, including the makeup air for the hoods, two issues will become apparent. Firstly, more or longer chill beam units may be required to handle the additional makeup air, which increases the system first costs. Secondly, the room air velocities may also become excessively high, as for every CFM of primary air sent to the active beams, around 3 CFM will be induced from the space. So for a lab that requires 10 air changes of primary air, the beams will induce another 30 air changes from the space, which will result in high velocities between the colliding air streams. In these situations, it makes more sense to size the chill beams just to meet the sensible loads, with the additional makeup air for the fume hoods being diverted to regular diffusers. This layout shows an example of how this could be achieved with a bypass duct. The bypass duct can be fitted with a pressure relief damper to allow the additional makeup air to pass into the diffusers without the need for a second VAV unit. In this next section, we will look at some typical water and airside system designs that have been successfully used with chill beam systems across North America. Let's first consider the water system design. The chill beams must be provided with chilled water that is warmer than the space dewpoint temperature, typically at around 57 degrees, but many buildings will also require low temperature chilled water for other processes, or may have a campus chilled water loop set at around 44 degrees. So a second medium temperature loop is often created for the beams. The secondary loop can be designed a number of ways. This layout uses a plate heat exchanger to create a closed secondary loop and is the preferred design for many engineers, as low temperature chilled water cannot be accidentally sent to the chill beams, potentially causing a condensation issue. The heat exchanger transfers heat from the chill beam return water into the primary loop. The secondary loop temperature is controlled with a three-way modulating valve, which allows some return water from the chill beams to bypass the heat exchanger in order to maintain the required chill water temperature to the beams. This design also includes two temperature sensors. The first simply controls the three-way bypass valve, and the second sensor is used for a thermal cutout circuit which shuts off the pumps if low temperature chill water is detected in the secondary loop. This ensures condensation will not occur on the chill beam cores in the event of a system failure or operator error. Here is an open loop design that simply uses a three-way modulating valve to blend return water from the chill beams with the 44-degree water from the chiller. This is a lower cost system, but there may be a chance that low temperature water could be injected into the chill beams accidentally, although the thermal cutout sensor and control should prevent this from occurring. This dual chiller setup is an ingenious way to improve system efficiency and build some redundancy into the system at the same time. During normal operation, chiller 1 is set to produce medium temperature chilled water for the beam loop, typically around 56 to 58 degrees. Running the chiller with warmer supply chilled water improves the chiller's efficiency by as much as 2 to 4% per degree of chilled water temperature increase. Chiller number 2 will produce low temperature chilled water for the DOAS air handling unit coils and other site process equipment that require low temperature chilled water. Should either of the chillers fail, or if one is taken offline for maintenance, then the remaining chiller reverts to producing 44-degree water, and a mixing valve, V5, will operate to mix the two temperatures to provide 58 degrees for the chill beams. Obviously, this is a more expensive design, so is better suited to larger buildings. Now let's look at some options for zone heating. There are several ways we can heat the space using active beams. Shown here is a single thermal zone consisting of 4 chill beams. The first method is to use a 2-pipe changeover system where the entire hydronic system will seasonally switch over to heating or cooling. Although low cost, this is unsuitable for healthcare and lab buildings that require year-round heating and cooling capability. The second option is to use 4-pipe chill beams. This allows simultaneous heating and cooling throughout the building, but note that each heating beam requires 4 water connections, so this design will result in a lot of pipework in the zone. Also note that more or longer beams may be required, as the coil in a 4-pipe beam is split into 2 smaller circuits, reducing the cooling capacity by around 10%. This third option makes use of a duct-mounted heater coil which sends warm air to the zone through 2-pipe beams. During heating, the chilled water valves are closed and the beams behave as induction diffusers, mixing cooler room air induced from the space with hot air from the zone heater. The reduced number of water connections and pipework in this design can reduce first cost significantly compared to 4-pipe designs. An alternative design worth considering is using 6-way zone control valves. The 6-way valve was specifically developed for use with chill beams and radiant cooling systems to provide 4-pipe functionality into 2-pipe zones. The valve body consists of a set of hot and cold water connections with a common 2-pipe out to serve the zones. All 6 ports are operated by a single actuator, which reduces control costs compared to the other heating options shown so far. This is how the 6-way valve will work in our 4-beam zone. When the actuator is in its 90-degree position, the 2 chilled water ports are open, sending water to the beams via the 2 common out ports. The actuator will rotate to the 45-degree position when the space set point temperature is reached and remains in the deadband with all 6 ports closed. When the zone requires heat, the valve rotates to the 0-degree position, sending hot water to the chill beam coils. One major issue to consider with this design is the fact that the water in the zone circuit will be returned into either the chilled or the hot water system. So 6-way valves are not suitable for systems that use different water treatments in the chilled and hot water circuits. In this next section, we will look at typical primary air handling unit designs for use with chill beam systems. But first, let's look at how the primary air system is actually sized. The chill beam primary air handling units are sized to meet the greater of the following 3 requirements. The ventilation rate to meet the appropriate ASHRAE standard or the required air change rate in the laboratory. The airflow rate that is required to remove the space latent heat. Or the airflow rate that is required to drive enough induction through the chill beam coils to cover the space sensible cooling. In high ventilation applications such as labs and patient rooms, the ventilation rate is likely to be the highest of these 3, so will dictate the primary air system sizing. One of the most common dedicated outdoor air system designs used with chill beam systems is a dual wheel configuration. The unit draws in outdoor air through the filter bank before it passes through the first heat recovery wheel, which transfers sensible heat from the return air to the outdoor air. During the cooling season, the heat recovery wheel pre-cools the outdoor air before it passes through the main chilled water cores where most of the dehumidification takes place. The air leaves the chilled water cores at around 53 degrees before passing into the passive desiccant wheel, which removes moisture and adds some sensible heat. The air is sent to the building at around 64 degrees dry bulb and a 48 degrees dew point. This dry and relatively warm air is useful for reducing reheat in chill beam system designs. There are several other heat recovery methods available. Here are just 2 examples. Air-to-air cross-flow heat exchangers which transfer heat from the exhaust air to the supply air in the air handling unit without any risk of cross-contamination. And runaround coils. These are useful for transferring heat from 2 separate airstreams that may be some distance from each other. These could be used to recover heat from the fume hood exhaust, for example. Finally, let's look at some typical control system setups for active chill beams. Zone temperature control is straightforward. This is a control sequence for a constant volume active chill beam design that would typically be used in a hospital patient room. Each thermal zone is fitted with simple 2-position all-modulating control valves. Modulating valves have some advantages over 2-position, including warmer return water temperatures back to the chiller. The hot and cold water valves regulate the amount of heating and cooling required to satisfy the room set point condition, with a deadband where both valves are closed. Note that both valves should be closed if the primary air is shut off during unoccupied mode. For variable volume applications such as laboratories, this control sequence would be used. The primary air flow rate is varied to satisfy the lab ventilation requirements, and the water valves will regulate the amount of heating and cooling required to maintain the set point temperature. Again, both valves would be closed if the primary air is shut off during an occupied mode, or if the primary air volume reduces to below the minimum flow rate for the beams to induce room air. As a rule of thumb, this happens when the pressure in the primary air plenum chamber in the beam falls below around 0.1 inches of water. Condensation prevention controls do not need to be complicated for well-sealed modern buildings without operable windows. This design uses a small number of wall-mount Dewpoint or RH sensors fitted around the building. Depending on the size of the building, around 2 to 4 per floor are typically used. The BMS will monitor these sensors and vary the amount of dehumidification at the DOAS to maintain the required building dewpoint condition. Additional condensation prevention measures such as pipe-mounted moisture sensors are rarely required and can often cause nuisance alarms. So to summarise, there are several case studies showing that reheat energy can account for as much as 30% of the entire energy use in a typical North American hospital. The revisions in the most recent version of ASHRAE Standard 170 allow the recirculation air changes through chill beams to count towards the total air changes, which will reduce the air system size. Active chill beams can be an effective method for decoupling the sensible loads from the ventilation requirements, so can reduce reheat significantly in applications such as labs and hospitals. There are now several healthcare buildings across North America that have used active chill beams to reduce energy consumption and improve occupant comfort, with several case studies being published online. Some of the major healthcare providers have set aggressive energy reduction goals for their buildings, so are now considering active chill beams as an alternative to all air systems. Thank you all for taking the time out to watch this webinar. We hope that the material covered today is useful to you and one more option for you to consider in your next healthcare or lab project. Our panel will now answer your questions.